AP Stats, this is Chapter 5, review session, take 2, or you could say the sequel. I don't think it's the prequel. Prequel means before, I think, but sequel is good. I hope you've been loading the yeast and getting it rolling today. And, man, I couldn't be any more excited than I am right now to be with you and to go through any questions that you may have. Here's the deal. This is going to be kind of wide open, free game, so to speak. I'm not going to spend a whole lot of time talking, but what I will do is just kind of address any questions that you have. Test is open. Some of you have asked for questions on the test, and we'll go over that. Also, if you ask questions related to the test, I'm going to exclude any review questions. We can go over those later. Just Chapter 5, because that's what the test is going to be over. Sarah, if you're watching this right now, had a great question. She actually texted me. Some of you saw that text. She asked me, Coach, how similar is the test in terms of this one to the previous one? Well, the content's kind of the content. And what I mean by that is if you did not understand something on the previous test, let's understand it, because I'll probably the likelihood of that occurring or coming up, maybe not the same question, but similar question, is very likely. So I want to make sure we address it, go through it, and hit these questions. I've already got 7 viewers down there. Man, that's rocking. And Sweden followers out there, I'm just grateful for you. Here's the deal. Coming off a long weekend, so I hope you're well rested. I hope you're ready to go on this test. Before we get started, I know I'm on a live podcast. This may be strange, but I don't think it's strange. Why not? I want to pray for you real quick, pray for us, and then we are going to get started. Cool? All right, God, you are good, and we pray for you even on this podcast as people are watching, whether it's live or not. Strengthen them, Father. Give them the strength to do the very best of their ability on tomorrow's test, and just help us to do better than our last time, God. And whatever happens, Lord, we trust you. We love you. In the name we pray. Amen. Let's get this rocking and rolling. 10 viewers. This is a record. 11. We are. I tell you what. I'm about ready to shed a tear. This is epic, of epic proportions. Just so excited. I just can't contain myself right now. This is so exciting. All right. So let's go to the questions here. I'm going to kind of get the link up and running. Some of you are posting questions, and if you are, please throw those down in the comment section on the right-hand side, and I'm going to pause this because hopefully, yes, just on the right-hand side, throw those comments down, and yeah, Eric, you can make some homemade bread in there, so yeah, go right ahead. Before we go into any of the comments on the right-hand side while you're kind of getting this rolling, I'll just start on number 1, if that's cool, largely just because that was one that many people struggled with, and it's an easy one. And it was probably one that I could have probably hit on a little bit harder, so I want to go through that together. This one says, you read in a book on poker that the probability about being dealt 3 of a kind. Let's see if this is. Let's see if I can. Hold on just a second. Let's see if we can. For some reason, this is. My pad's not working. Let me see if I can get this going. But it says in a poker game that the probability of being dealt 3 of a kind in a 5-card poker hand is 1 of 50. All right, is this Wacom tablet messed up here? It's not letting me kind of go here. Okay. I don't know if y'all are seeing this or not. All right, hold on just a second. Might have to restart this bad boy and then we'll get it rolling. I'm trying to get this thing. If you want to, you can kind of probably fast forward the next minute or so of this. All right, it's not working right there. I'm trying to see this with my mouse here. Yeah, it goes all the way to that corner. My apology, y'all. Try to see this one more time. Wow, that's funky. Okay. That is not me down below. I'm trying to see what has happened. Okay, let's see here. All right, I might have to do this by hand, y'all, which could be very entertaining. So join the party. Here we go. Yeah, I'm gonna have to do this by hand. But we'll be flexible. Man, we are dedicated, aren't we? We're dedicated. So let's take a look at this and we'll check this out. All right, it says you read in a book in a poker that the probability of being dealt 3 of a kind in a 5-card poker hand is 1 of 50. What does this mean? Well, remember with probability, if we looked at this, probability is never guaranteed, but we do say that over the law of large numbers that the true probability will be approached over the course of time. So being dealt 3 of a kind in a 5-card poker is here, which doesn't mean that for every 50 that I'll have 1, because it could be that I have more or less. But over the law of large numbers, over the course of a lot of hands, this should approach 1 of 50 or 2%. So as I look at this, anything that says if you deal like C says, if you do deal 10,000 poker hands, then 200 of them will contain 3 of a kind. Well, that may not be true, but we would expect that it would approach 2% pretty close. The best guess is that's not true. It's not a best guess. It's more a probability. It's a theoretical probability where it's approaching this 1 of 50. And we're saying that that over the course of thousands of poker hands, that's why A is correct, that it will approach that 1 of 50 that's there. Cool? All right, sweet. Some of you have questions, so I apologize. We're going to keep this rolling. Perfect. Lindsay, I see your questions there. Let me get to these bottom ones, and then we'll go from there. Yeah, Brianna, it's not working, but we're going to do the best we can with what we've got here. Cool. I think we'll be fine. Ryan says, can we see everything? Wouldn't want to repeat of last time. Yeah, well, we're going to do the best we can to try to show as much as we possibly can on this. I may hit some of the test ones, and then some of the review ones we can hit later on tomorrow as well. That's there. Lindsay, let's do this. Before I get to the review, let me look at your questions. How being independent affects probability of events. Okay. All right. So let me see here. Okay. So if I were to, let me see, backtrack. Okay. I think that there was a formula on this right side of this flip chart. Let me see if I've got everything still up and running. It may not be. Yeah, I don't think so. Okay. So remember that with the formula that we came up with, one of the main formulas that was important was this idea of it was the probability of A and B, and it was equal to the probability of A. Make sure, and I had it here. Well, let's talk about this. The probability of A and B is equal to the probability of A times the probability of B. Now, this is true when we have something that is, and I'll just put it down here, that's independent. The reason why this is independent is because the probability of A and B is something, and you got to think of this differently than mutually exclusive, right? We could talk over that later. But this is referring more to the fact that probability of A can be multiplied by probability of B because probability of B has no effect on, or has no change on, what happened to the probability of A. You say, Coach, what are you talking about? Well, let's take the example of this here. Let me erase this. This is crazy. Okay. If I say, what is the probability of, let me do a different color, 2 free throws, okay? And let's say that, what is the probability of making 2 free throws? It would be this would be equal to, making 2 free throws. This would be equal to the make of a first times the make of a second. And if I was an 80% free throw shooter, I would say 0.8 times 0.8. The main reason why is because the second has no impact on what happened on the first. This is independent. Therefore, it relates to the above white formula. But take the example of, let's say, what is the probability in 2 cards of drawing a king and, sorry, I'm just doing this, we can see, and a black card without replacement. Okay. Now, what does this mean? The blue one refers to an event that would not be independent. You say, Coach, how is that? How does that even work? Well, think about this. Drawing a king, let's talk about that one first. Drawing a king, there are 52 total cards, right? Sorry, this is by hand, so if this is ratchet, I apologize. There are 4 out of 52 total cards that is representative of a king, right? But I don't multiply then by what the probability of a black card is, which would be 1/2, because when we look at this without replacement, one of the cards was a king, right? So, and just to make this a little bit better, because we can get into really in-depth stuff. Let's say it was a black king. So what we're going to say is, out of the red and out of the black, we're going to say that 2 out of 50 was the probability there, okay? So assuming that we got a black king, we would then say, what is the probability of the second card being just simply a black card? Well, now since we did not replace it, we have a 51 total cards. And now instead of 26 total black cards, because one of those cards we chose was a black king, we now have 25. We see the example right here of the probability. Let me see if I can actually draw over this. Let's see here. Let me put this on there. Perfect. I hope this makes sense. This is the probability of A, but then it's not multiplied by the probability of B. It's the probability of B, and then given that A occurred. Should be a straight up and down line, but given that A occurred. So this would be 2 times 25 and then divided by 52 times 51. This would be a dependent event because what happened over on this right one changes based on what happened on the first one. Where the yellow one is independent, the blue one would be dependent. Now, if I did replace it, this would be then a dependent event, which would then change in terms of what we were looking for there, okay? Perfect. Okay, awesome. Let's keep rolling. Number 5 is the first one on the test, actually number 2, and then I'm just going to keep rolling if that's okay. Number 2 says this, with all of that being said about independence, it says the probability of A and the probability of B are given. What is the probability of A or B? Okay, so here's the question. What we're trying to find is what is the probability of A or B? And that U thing, by the way, is or, and then the overarching symbol, by the way, this right here is and, okay? Okay, so this is and then this one's or. So I'm going to use or mainly because I'm writing here and typing. But this is equal to, based on the rule that we have on our flip chart, which, by the way, you can use tomorrow, is the probability of A plus the probability of B minus the probability of A and B. Okay, so this is by definition what we know to be true about the OR formula. Okay, but then it gives us something different. It says that A and B are independent. Now, if they say they're independent, notice this like normally I would say just understand and kind of work through it in terms of the diagrams and that sort of thing. But you got to kind of forget that on this one because this is straight formula point. It's straight formula. So this is the definition of independent. So what it does is it says probability of A and B is the probability of A times the probability of B. So we really, because of what they told us, can replace this with minus the probability of A multiplied by the probability of B. We could put that right here, okay? And that's it. And then what we would do is then we would, this obviously is what's down below, but we would plug in 0.25 and 0.34 and for P of A and P of B, and we would solve accordingly. And once I do that, then I could plug in and solve it and rock and roll. Cool. All right. That's number 2. Number 5. Let's keep going. Yeah, this one's a good one as well. It says, given the probabilities, okay, probability of A, but then again, it brings back this whole idea of what is the OR. So kind of going back here, I'm going to kind of copy and paste this formula because we know that the OR formula is listed here. And when I plug this in, since this is the OR, we know that 0.7 can be plugged in for A or B. It doesn't say it's independent yet. Let's see if it does. But then it says, what is the probability of P of B? So we're really looking, and then P of A is 0.3. Sorry about that right here. So what is the probability of P of B? Okay. Now, 2 things. It says A and B are mutually exclusive. A and B are independent. Okay. Now, a couple of things on this. We know that P of B is our variable X, right? That's what we're solving for. So we'll put this here. But the problem is that what do we do with this probability of A and B? That's the question, right? And it's a good one. We're like trying to figure out what we do with it. But it gives us some hints that, number 1, the first question is it's mutually exclusive. Well, when we know that mutually exclusive, we know that the probability of A and B is 0. You say, Coach, how is that? Please show me the way. And I appreciate the enthusiasm on that. It's because the Venn diagram, when it's mutually exclusive, would not have a center, right? There'd be 2 separate circles, meaning that the mutually exclusive would produce a 0 for the intersection. So this would be minus 0. And so this would be gone like a freight train. I would subtract 0.3 to get X by itself. And when I did that, I would get 0.4 as my answer, okay? So we cancel out here, we cancel out here, we cancel out here, leaving us with the answers of A and B as our possibilities. So then we backtrack and say, okay, well, just based upon what they gave me again, let's write down what we know. The second question, based on what they gave me, is it's independent. Well, like I said earlier, independence on the previous problem down below in white states, and I'll put this down here, independence states that A and B is A, probability of A times probability of B, which we could sub in here, okay? So we're just going to plug this in. And so what we're going to say is this would be the probability of A times the probability of B, based on the fact that it is, sorry, doing this by hand, y'all. Coach J's okay, by the way. If I start going crazy, that you can't read my writing, I'm okay, all right? I am okay. So this would be what the definition of independence would be here, okay? So we've got 0.7, still the OR. 0.3 is still the P of A plus X, right? But now what we can do is we could plug in what probability of A is. So this could be, let's subtract 0.3 here, okay, just like it did before. So this would be 0.7 minus 0.3, which would be 0.4 equals X, which is this part here, minus probability of A is 0.3. So minus 0.3 X, because probability of B would be that as well. And so we would say X minus, or this really is 1X, right? 1X minus 0.3 is 0.7x equals 0.4. Divide by 0.7 each side. And we would end up getting 4/7, which would give us the answer of P. So based on my formulas, I literally I use what they have given to me, and then I use that to be able to execute whatever X I'm trying to find or whatever value I'm trying to find on that one. Cool? Cool. Oh, man. I hope that made sense there, Lindsay and Hannah, because number 5 was a tough one. Yeah, we'll go over the FRQs on the test as well. If I do not get to your question, it's not that I don't like you. It could be that you like Ohio State, or no, I'm just joking, Ryan. I'm sorry, that was mean to me. Because I did answer your question, so I got you. But no, it's mainly because of just time. So I'm just trying to rip through these as quickly as I possibly can. So just hold on tight as we go through them. Okay. Cool. Number 6, let's go through that one. Sorry, I just got a taste of a banana. Sorry about that. All right. An athlete suspected of using steroids is given 2 tests. They operate independently of each other, okay? Test A has a probability of 0.9 of being positive if steroids have been used. Test B has a probability of 0.8 of being positive if steroids have been used. So really what we have is the probability of A, the fact that steroids have been used has a 0.9 probability, and the probability of B is 8. Okay. Based on this, what is the probability that neither test is positive? Now, what they've done here is they've come in with a complement, because now it's saying that neither test is positive, meaning it would be the counter of that. So what is the probability of a complement, which is like the little C on top? I know it's on the bottom, but that would be equal to 0.1, and the probability of the B complement with the little C at the top would be equal to 0.2. Now, since they are operate independently of each other, independent says that we can use this. So what is the probability that this occurs and this occurs? Well, that's where we would use 0.1 times 0.2. And so the fact that both of them would be positive, or was probably that neither would be positive if steroids was used, would be C, 0.02, because 0.1 times 0.2 would be 0.02 in that context. Cool. No, I wasn't trying to roast you, Ryan. You know I care about you. Oh, Brianna, what are you talking about? Like, what are you confused on? I'm sorry. Sydney, you said you're confused. I'm sorry. I'm trying. I know it's crazy with the pad not working. When do you multiply probabilities and when do you divide them? All right, let me see something here. Let me see. I want to go to something. I want to just try something different here. Could teach this. Hold on just a second. So 6. I'm seeing if this one's different. I'm looking at the review sheet real quick because Lindsay had some questions, 31, 35. So I'm looking at some of the multiple choice as well, just to see where we're at. To answer y'all's questions, I think the big thing. Okay, so I think the big thing for you to understand is when we approach these questions, we've got to highlight specific terms, okay? So for instance, let me backtrack here, okay? First of all, it gives this and this, right? Hold on, backtrack, do this. Okay, so it gives me this and this, right? Now, that right there, if I'm going to a question, that doesn't really help me, right? That tells me what I plug in, but it doesn't really help me with how I execute it. Now, when I look at these questions and I notice that, for instance, they give me this, I'm stopping right there and I'm drawing and I'm putting down, especially if it's a multiple choice, I'm putting down what the formula is, which is strictly this right here, okay? Now, after this, once I've executed and plugged those in, I then keep going with the problem and say, okay, I know that, for instance, 0.25 goes in for this. So this one's checked off, right? I'm trying to find what this is. Like, that's my answer that I'm trying to look for, because that's what it said what is. I know that the probability of B, I've got that one based on what is pink over here. So really the part that's in question is this A and B part. But if it says that something is independent, we remember that based off not only our flip chart, but by definition, it's the probability of A times the probability of B, because there is no matter what happens in A, it doesn't affect what happened in B. And so based on this formula, I noticed that this is the same as what is over here. So I plug it in for right here, this part right here. And then once I substitute them in, it makes it easier to solve for the OR part. Over on number 6, and really number 5, number 5 is basically the same question that I just stated. The only difference with that, it gives us, okay, it says probability of A or B is this. So again, because I see it there, I list what the formula is, right? Now in pink, I'll kind of show you here. What has been given? Well, I've been given this and I've been given this. So let's plug it in, because A or B is 0.7 and 0.3 is probability of A. I'm solving for the probability of B. So that's kind of what my focus is on, right? Because that's what it stated. But then it says, what is this probability of B if it is mutually exclusive? Well, we look back in the podcast and notice that if it's mutually exclusive, there is no and, right? This can actually be eliminated, making it easy to solve for. When it's independent, like I did on the previous example over here, I noticed that this is the definition of independence, and I could plug in this probability of A times probability of B in for A and B for my second one, and then I can solve for the other one that's there. Number 6 looks at independence, because it says both of these are independent. Test A has a probability and test B has a probability, but it asks the counter question is, what is the probability that neither of them will be positive, given that, knowing that they use steroids, right? Well, if the complement will be 0.1 and 0.2, since these work independent of each other, we can simply multiply, right? Because one doesn't affect the other. So 0.1 times 0.2 is 0.02. So knowing how to go backwards with these formulas are essential for your understanding and really your execution on the test, okay? Hope that helped. I'm reading here now. Kristen, did that make any sense? Sydney and Brianna, did that make some sense? So the big thing, I hope you know that why these 3 are not correct based on the 0.4, right? But you've got to understand that what is independence, right? Independence is literally this definition here. And it's not just enough for you to know that. You got to understand the context of it. You also need to know that, like for this one, when you were working backwards, that how do I plug that in for something, right? Things like that is very important. Number 5 and number 2 are very similar. And so I could see why if you missed number 5, you might have missed number 2 as well. Okay. All right. Perfect. If you need me to, and you're still confused on those, we can look at those tomorrow as well before class. Okay. All right. Keep hanging in there, y'all. Keep hanging in there. All right. So here's the one thing on number 7 that I noticed. People got confused because it didn't say at least one. I'm going to look at one here in a second that is just a little different from that. But if I say at least one, that is different than what I just said here. It says an instant lottery game gives you probability of 0.02 of winning. Plays are independent. Okay, what that means is I can just simply multiply the probabilities by each other. because one won't affect the other, right? So we just multiply the probabilities. If you play 3 times, so 1, 2, 3, each of those will be there. We just, again, are multiplying. What is the probability that you win on none of your plays? Well, the probability of winning is 0.02. The probability of not winning is 0.98, right? So if I multiply 0.98, again, the probability is independent. So 0.98 times 0.98 times 0.98, or 0.98 to the third. What do we get? We get 0.98 times 0.98. And I'm just doing this here just so I can remember. And I got 0.94. Yeah, so that's why B would be the correct answer. Many people were confused because they looked into it way too much here. They looked at the at least one part. So if you look at number 31 off the review, which I think is the one Lindsay is looking at. Shout out, Lindsay. By the way, shout out to all of y'all that are out there. I don't know how many viewers I have right now. I have 13 viewers, y'all. I've never had that before. This is a beautiful moment. I just want to say thank you to everybody who supported me through this. It's been hard. All right. Let's look at number 31. All right. Starting to get that time of night. I get crazy. All right. Ignoring twins and other multiple births, assuming a baby's born, are independent. So the probability that a boy is a boy and the probability that a baby is a girl both equal to 0.5. Okay. All right. Here we go. Use this. The probability that at least one of the next 3 babies is a boy. Okay. So let's talk about this. 30, number 30. Let's look at the differences. The probability that the next 5 babies are a girl. Okay. Each are independent from each other, right? Wouldn't this each be like, if I were to do this, this would be like, let me put this up here, right? This would be like 0.5 times like 0.5, right? Times 0.5 times 0.5 times 0.5, right? So each of them are separate. It'd just be 0.5 to the 5th. But this next one says the probability that at least one, now here's the key, okay? Here's the highlight, ready? At least one. Notice the difference between this and what we just said, that you win on none. That is not the same. So please know the difference. At least one, you got to be careful on this, because on this one, you've got to do 1 minus the probability of none, okay? And what is the probability of none? That means that none of whatever we were asking would occur. So at least one, the counter of that would be none, right? Does that make sense? Counter of at least one would be none. The probability that at least one of the next 3 babies is a boy. So the only possible outcome that we could have would be girl, girl, girl. Wouldn't that be right? So the probability, like the counter of that would be girl, girl, girl. So the probability of none would be 0.5 times 0.5 times 0.5, right? That means that girl, girl, and girl, right? Cool. No other possibilities. And then once we're done with this, we take 1 and subtract by 0.5 times 0.5 times 0.5. And when we do this, we get, I think this is like 1 minus, I'm doing this in my head, so I'm sorry, 0.125, which is 0.875. Oh, 0.875. Oh, look at Gucci. Coach J, number or letter E. There we go. And that's how we would attack that. Cool. And that's the difference between those there. Awesome. The yeast is rising. Do you feel it? I love it. You might leave for that, Charles. Very good. I hope you're having a good night tonight. There's my falsetto right there. Yeah, we're salty. All right. Too Gucci. I love it. We're having too much fun tonight. Oh, yes, Hannah, we're doing did I do number 7 yet? I think I did number 7. Maybe I didn't. Yeah, I think I did. Hannah, let me know if any of these are not working. Please let me know, okay? And yeah, we'll go through those together. 11 and 12. All right, 11. Yeah, I don't know how to do number 11. No, I'm joking. I'm messing with that. You're like, Coach, you're crazy. You are right. I 100% understand that. I agree. All right. Okay. So okay, let me go back here. Where are you? Yes, you. Okay. Okay. I want to pull this up. Okay. By the way, this is on our formula sheet. So as I do this, just as a quick heads up here, this actually is working well tonight with the typing. All right, so we're going to do this. This is the formula. If you're like, Coach, that doesn't make any sense, let me show you. So this is the formula for dependence, right? And this is the formula for independence, okay? So dependence and independence. The formula that you'll see on your formula sheet takes this one, just so you know. So your formula sheet and your flip chart are two different things. You can have both for the test tomorrow, but just know that in the future you'll need to know like how to use the formula sheet a little bit more as well. So just a heads up on that. So if I were to say what is the probability of A and B, we would say that it's equal to this right here, right? The one on the formula sheet, I believe, has it says the probability of B given that A occurred is equal to the probability of A and B. Sorry. And B, all by hand, y'all. Look at this. All divided by the probability of A. Cool. And you say, Coach, how did you find that? Well, really, it's this. I hope this makes sense, that probability of A, whatever happened in A, would affect what B would become, right? We talked about the king and the black card, right? Things like that. Well, what I did was I just divided by probability of A, and that's how I got over here, right? So I just wanted you to be aware that this is the one you'll see on your formula sheet. However, on your flip chart, you probably have this one, which is sufficient for the dependence. So I'm going to use this one mainly because this is the one that we've been using, but just know that this one is the same, even though it looks a little different. Okay, so here's what it asks. It says the conditional, an event A will occur with probability of 0.5. Again, I'll highlight these, okay? An event B will occur with 0.6. And the probability that both will occur is 0.1. The conditional probability of A given B. Okay, so what is the probability? This is the question here. What is the probability of A given that B occurred? Okay, so really that's the question that we're trying to ask, right? But notice that this right here is just a little different, right? Just a little different here, and we've got to figure out, well, what's occurring on this one, and kind of rock and roll on this, okay? So what we want to do is the conditional probability of A given B would be this, but it's a little different here if you noticed. But what we can do here is just kind of flip-flop these variables and say, what is the probability of B and A? Just a little different. It would be the probability of B, probability of A given B. Okay, so really what we have here is the probability of A given B is what we're trying to find. The probability of B is 0.6. And the probability of B and A, or A and B, both are the same, by the way, would be 0.1. So we put 0.1 here. Okay. So once we plug this in, we would solve this, and we would then divide by both sides by 0.6 here. So divide by 0.6, divide by 0.6. And the answer for this would be 1/6, because I would just divide by that to get this by itself, and there you are. Points would be 1/6. Again, making sure that the formula we're plugging in appropriately, and then rock and rolling from there. The question is are these events mutually exclusive? Well, they're not mutually exclusive because they have an and, right? So if a Venn diagram of, sorry, Venn diagram, if a Venn diagram occurred, the and in the middle would be 0.1. Cool. So that's that there. So just as a heads up, this is not mutually exclusive. Now, is this independent? That's a whole nother ball game, because then we say, well, based on independence, if it really is truly independent, the A and B would be 0.1. The probability of A would be, what is it, 0.5. Probability B is 0.6. 0.5 times 0.6 is 0.3. And that's not equal, so therefore it would be dependent. It would be the orange formula, and so it would that's how we would show that there, okay? Oh man, thank you, Rita. Appreciate the falsetto was beautiful. Thank you. Sydney, I was in choir. I'm a coach, I know, but I was in choir and I played handbell. So Sydney, I'm all game with the choir stuff. You know what I mean? I give it. Brianna, are you not having fun? What's going on? Talk to me. If you got questions, throw them down there. If it's something that I'm going too quick on, I'm trying to go through a lot of questions, and I want to make sure that I can do that there. Cool. Yeah, Sydney, I've got my gloves. I got white gloves from my handbell days. I'll have to bring them in and teach with them someday. You know, I always had the little tiny bell, so it was like ding 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 ding. It was cute. It was cute there. So it's good. I'm waiting on some other questions, and Brianna, I want to just wait on yours real quick, specifically because we are approaching the end of this one with number 12, and I want to make sure that I hit on those questions. So I'll do that. Brianna, I can always come back, but what we can do, let's look at the FRQ on number 11. Okay, so this one might be challenging because I'm going to do this all by hand, but we'll try. It says, suppose that 8% of the patients in a small town are known to have heart disease. Okay, so stop. So out of the whole town, right, 8% has heart disease. So if you can think of like, okay, this is 0.08, right? And therefore, not heart disease would be NHD, right? And this would be 0.92. All right. It then goes on to say, and suppose that a test is available that is positive in 96 of the patients with the heart disease. So the test with the heart disease is positive in 96% of those that take it. Okay. That means that it is negative for 0.04 of those that take it. So that means 4% of people that have heart disease, the actual test would come out as negative, even though they do in fact have heart disease, okay? Now, for those that don't have heart disease, but they still take the test, 7% would have the positive, even though that would be incorrect, and 0.93 would have a negative. So now, since I've set this up, we know it's a tree diagram because there's two variables of whether you have heart disease or not. And then the second one is related to whether it came up positive or not, okay? Yeah, good question, Lindsay. We're taking the whole test over again, just as a heads up, but it's strictly over chapter 5, okay? So everything will be the full test again, okay? With corrections, you can still have the corrections there as well, okay? So yeah, that's okay. All right, so the question now becomes is what is the final probabilities that are here with all four of these? Now, I'm not going to go into all the logistics of every little calculation, but we remember we can find the calculation by doing 0.08 times 0.96 to list it here, 0.08 times 0.04 to list it here, and you would list all four of these, which should all add up to be equal to 1. Okay, should, if I didn't make a mistake. So is this the part A, find the probability that someone who, the person tests positive for heart disease. So the only ones that would exist from would be here and here. So what we would do is we would take this spot plus this spot, and could be this top spot or the bottom one, not the ones that are negative. And so we add them together. And when we do, I think we get, is that the 0.14? I think it's the 0.14 that we get there. And that's how we would add them up. Now, the next part asks, if a person is selected at random and given the test, and it comes out positive. Now, the fact that they gave this to me tells me that the negative would actually be excluded, because what's happening is what is being given is the fact that it's positive. It's really the answer to what we found up on top, which was, I think it was 0.14. Don't quote me on that, but I believe that's true. So we then say, based on this part, right? So based on the part that's given, or the part that we're focused in on, the question is what is the probability that the person actually has heart disease? So what is the probability that they have heart disease over the given? So we're talking about just this top part, not this one here. And we're not talking about the 0.08 because we're only focusing on the ones that are in orange because it has multiple variables, okay? By the way, these are dependent events, right? Notice the probability of the test coming out positive is higher for those that have heart disease than those that do not. So it's a little bit different. So we're going to take this probability over my total, what I found up here. So it'd be whatever this probability is over my given, which would be my total from up here. And that's how we rock. It'll be here. That would go right there. Cool. All righty. All right, let's go to the next one. Let's go to question 14. Question 14. Okay, so 14 focuses on this. It says I think most people actually got this top part pretty good. The dice rolled once. The number turning up is observed. 2 and 5 have 3 times the likelihood, right? So when we looked at 2 and 5, this would be 3 out of, I think it was out of 3 out of 10, right? Or this would be 0.3. This would be 3 out of 10. This would be 1 out of 10, right? 1 out of 10, 0.1. You could put 0.1 or 1 out of 10, okay? So the question then comes out to, let A be the event, the number rolled is a prime number. So what is the probability that we would roll a 1? Let me see, what does it ask actually? Find probability of rolling a prime number. So probability of 1, or let me extend this. Probability of 3. Probability of 5, right? So what I can do here is, and because it's or, we just add them up. So we would say 0.1 plus 0.1 plus 0.3. So I got 0.5. 0.5, that would equal. Cool. And I would actually put a little context. 0.5 is the probability of, and I would even put this here, the P of 1, P of 3, P of 5. 0.5 is the probability of rolling a prime number, okay? The next one is let B be the event. What is the number? Number rolled is an even number. Okay, so I would say, okay. Oh, hold up. I forgot one, didn't I? The number rolled is a prime. Prime number, I forgot probability of 2, didn't I? So I need to put that in there. Put that in there. Boom. So that's 0.8, I think. 0.8. Yes. Because, oh, no. And then 1 is not, it says. 1 is not prime. So this would be 0.7. That's right. Okay, so it should look like this. My apology. It says the number rolled is even. So that would be where we would do this here. that would be the probability of 2 plus probability of, and again, I would describe this afterwards. You don't mean it's not going to hurt you. And give you more context there. Just putting an answer though doesn't really work. Okay, so you have to kind of show this, and then maybe state what that would be there. Okay, so 2, 4, 6. Let's be 0.5. Okay, determine if the events are disjoint. Now, these events are in fact not disjoint because it's possible to have the probability of a 2 that's rolled, right? It's possible to have a 2, which would be both event A and B, right? And so just giving a counterexample would be sufficient. Just make sure you go into detail about that. That would be part D. Part E, it says determine if they're independent. Well, independence, we remember. Again, once I hear independence, I'm putting down that formula every single time and then trying to show whether that would be true or not. Okay, so let's see here. So here's this. I'm going to kind of move this up here. There we go. Delete this. Are they independent? So here's the question. If this is true, then we're good. So the probability of A times the probability of B would be 0.7 times 0.5. Now, where is the probability of A and B? What would that be? Well, where does A happen and B happen? Well, A and B would be, the only thing that would happen would be 2, which would be 3 out of 10. What wasn't it? It was like 3 out of 10 or 0.3. So we would say 0.3. Does 0.3, where the probability of 2 would overlap with the probability of 2 in each one, would 0.35 equal 0.3? And the answer is no. Therefore, these are dependent events based off the formula. And therefore, knowing that the probability of A occurred would affect the probability of B. Okay. Cool. All righty. Awesome. I hear screaming. I hear laughter. I hear fun and excitement on this study session. And as you should. Man, we went through almost the whole test there, y'all. A couple quick questions that I see as I'm going through there. And by the way, come in early tomorrow. I would love to look at some together with you. I hit 31, I think 35 and 37. Lindsay, let me look at this, okay? 30, 37. 35 is a tough one. $35, I'm going to skip, Lindsay, largely because it confused people more last year. I remember doing that one. I'm going to skip that one, 35. So skip that one in your mind. Oh, man, yeah, 37. If you look at 37, oh, my word, that is a phenomenal question, okay? 37 is phenomenal. In fact, if you want to, pause my video and try this one out. I'm gonna do this one, okay? It's cool. I'm gonna do it. Let's get after it. Okay, let's do this. Let's go here. All right, it says this. Let me see here. Kind of similar to this one, isn't it? Very similar. Yeah, it says, suppose that A and B are independent events. Okay, remember independent. It says, what is the probability of A or B? 0.2 is P of A, 0.4 is P of B. Fact that they're independent, remember this is what's in white, right? We start with A or B. So we have probability of A. This is the formula given. But because it's independent, we can substitute this in for this. Once we do that, we can just simply put 0.2 and 0.4 in and then go from there, okay? So hopefully that helps you there on that one. Lindsay, tomorrow morning I'll be there at 7:30. So come in early and get it done. Lindsay, what are you thinking? Yeah, Brianna, here's the deal. A question. What I went through today, what are you not getting? And what I mean by that is I don't want you to say everything because I think there might be a common theme. Is it the formulas? Is it how do I use the formulas? Is it the formulas? If I say something's mutually exclusive or something's independent, is it understanding that? What are you thinking? Just real quick as we wrap this up. Kind of do this. Kind of throw this down here. I want to make sure I kind of get just a little bit. I got 11 viewers on tonight. I appreciate y'all, man. I really do. I know we're battling through this. I know this can be tricky. It's not like it's an easy test. And so the best of your capability is all I can ask for, okay? So I just real quick as we wrap up, coming in tomorrow will be huge. Really just doing the best of your capability. That's all I really care about and all I really that's it. Lindsay, don't drop out of high school. Come on now. You got this. You got this. Hey, just know I care about you. I love y'all. If I were to tell you, if I was like, hey, what's one thing that you could do? I think just going through those multiple choice questions and doing those is key. Tomorrow, here's the deal. Listening to me, it's valuable. It really is. I try to be a source to you and let you know that I'm here for you. I'm for you. But the biggest thing I'm telling you, and this is a college thing, y'all. This is not just like Coach Jay's AP stats. When you get into tougher classes that make you think and make you have to reason and not just regurgitate stuff, the best thing to do is to simply to do it on your own, but then to explain it or talk through things with your peers. I'm telling you, people think I'm crazy about that, but that was the biggest difference when I saw my grades increase when I went to college. It wasn't like I got all smart or anything. It was literally the way that I studied. It wasn't me listening, watching podcasts again, though that may be helpful. The biggest thing is partnering with people to really help and support you together. And so I know I'm preaching, but I'm just trying to help you out however I can on that. No, I love you, care for you. Peace out, homies in the hood. Yeast out. Be good. Take care of yourself. Take care of other people. Love y'all. Bye.